Yeah. Good morning, everybody. So I'll talk about representing Boolean functions using polynomials. This is joint work with Arkadev and Shachar Lovett. So let me start. So we'll be working with Boolean functions. Think of them as encoding your favorite problem. Okay. And given a Boolean function, we can think of them as vectors in a vector space of dimension 2 to the n. And once you think of them as vectors, you can choose your favorite basis, decompose that Boolean function into that basis, and study the properties of Boolean functions looking at the decompositions. For example, the standard basis will correspond to truth table representations. Okay. The two important bases that people have studied in literature are this AND basis, where your basis functions are these AND functions on subset of variables, also known as, this basis is also known as De Morgan basis. And as you can see, decomposition in this basis will correspond to writing the multilinear polynomial for your Boolean function, right? Another important basis which everybody is fond of is parity basis or Fourier basis, where your basis functions are parity functions. Okay, this is very nice basis because it's orthonormal and it has all kind of patterns which can let you infer all kind of combinatorial properties about your Boolean function. And again, decomposition in parity basis is also same as writing the multilinear polynomial, but instead now you think of your domain as -1, 1 to the n instead of 0, 1 to the n. This is just a linear transformation between the two bases. Okay. And once you think of them as polynomials, there is a natural way of measuring the complexity of Boolean function, that is through these polynomials. Okay. I can define these two measures, degree and sparsity, but the degree of a function will be the degree of the corresponding polynomial. Sparsity will be number of non-zero terms in your polynomial representation. And I can define this degree and sparsity measure for both the bases, De Morgan basis and the Fourier basis. And as I said, there is a linear transformation between the one basis to other. So degree is same in both the bases. Okay. Although sparsity can vary drastically depending on what basis you're working with. For example, AND function has sparsity 1 in the De Morgan basis, obviously. But in the parity basis, it will have sparsity like 2 to the n. Similarly, parity function obviously has sparsity like 2 to the n minus 1. You can write these things out yourself. But the parity function in the parity basis obviously has sparsity just 1. On the other hand, OR function has sparsity, maximum 2 to the n minus 1. In the De Morgan basis, it has sparsity 2 to the n in the parity basis as well. As you can see, sparsity can change drastically between the two bases. Okay. So I've defined how to represent Boolean function using polynomials. The other thing that we would want to do is use approximate polynomials to represent Boolean function. So in classical approximation theory, representing functions, pointwise approximation of function using polynomials has long been studied. And Nisan and Szegedy introduced this notion to studying Boolean functions. They define this notion of approximate degree, where you look at all the possible polynomials which are approximating your value within a small error. For example, within an epsilon error, your polynomial is representing your function. And then among all the polynomials which are approximating your function, you choose the one which has minimum degree. That will be the approximate degree of your function. For now, think of epsilon as 1 by 3. It doesn't matter as long as it is a small constant. Nothing important will change. Since its inception, there have been a lot of application of approximate degree. There is application in query complexity. There are application in communication complexity of some special lifted functions. There are application in differential privacy, learning theory. So it has been a very nice measure which people have utilized across the domains. And similarly, we can also define approximate sparsity and approximate in the De Morgan basis and approximate sparsity in the Fourier basis, as we have defined the approximate degree. And once we have defined these two ways of measuring complexity using polynomial and approximate polynomial, we have these two natural questions. What is the relationship between degree and approximate degree? And what is the relationship between sparsity and approximate sparsity? So what do we know in case of degree versus approximate degree? There is a celebrated result of Nisan. There's a remarkable result which shows that for every Boolean function, degree and approximate degrees are polynomially related. Um, this says, degree is easy to find out, right? You can just write the polynomial and you'll know the degree. Approximate degree is not that easy to argue about, even for simple functions like OR and AND functions. What this says is that if you know degree, then approximate degree cannot be too small, right? Yeah, it has been optimized. I'll just say this. And later on, this was early 90s when Nisan and Szegedy had this result, and later on, late 90s, there was this implication by work of Beals, Bormann, Cleve, Musto, and Wolf. Using this relationship and more work, they showed that quantum and classical query complexity are equivalent up to polynomial laws. So they managed to show that this quantum and classical world are same through this approximate degree relationship, via this approximate degree relationship. And very recently in 21, Aronson, Ben David, Kothari, Rao, and Tal gave a tight relationship between degree and approximate degree, which is quadratic. And this is tight, which is witnessed by OR and AND functions. So this problem, degree approximate degree, is kind of resolved in a very satisfactory sense. What about sparsity? This is a question we would be interested in. In case of Fourier basis, we know that approximation can give us significant advantages. This we know. The folklore results or work of Rasborov, Sominsky tell us that for AND function and OR function, the sparsity is just order n, but approximate sparsity is order n. But we know that sparsity of AND and OR is like 2 to the n. So we can get significant advantage using approximation in the Fourier basis. So in Fourier basis, there can be very large separation between the two measures. In case of AND, again, we can ask the same question: can we have very significant separation or not? We can get some savings. For example, we know that degree of OR is theta root n, and which tells us that sparsity cannot be more than n to the order root n. And the sparsity of OR function is like 2 to the n, right? So this gives us some savings. You can say it's an exponential savings, but on the log scale, things still looks polynomial, right? If I take log of approximate sparsity and sparsity, I'll get root n and n, right? So on the log scale, things are still polynomial. So one can ask, and it seems like log is the right scale for sparsity and not without log. So what about log sparsity and log approximate sparsity? Can we say that in this log scale things are polynomially related, or there is nothing we can do? What is a case in case of De Morgan basis? And although it's a natural question, studying the relationship between sparsity and approximate sparsity in De Morgan basis, but there are some motivation as well. As degree is related to some query models, log sparsity in De Morgan basis is also related to some query model. I'm not going to say what the query model is. And moreover, understanding this log sparsity in De Morgan basis was very crucial in understanding communication complexity of AND functions. These are functions lifted with 2-bit AND gadgets. Okay, and they were very crucial in resolving log rank conjecture for AND functions. This is work of Noop, Lovett, McGuire, and Guan from 21. And in their later survey, they conjectured that in De Morgan basis, we don't expect that approximation can give us significant advantage. So this was their conjecture, that on log scale, we feel that things are polynomially related for De Morgan basis. And this is our main result. We show that indeed this is the case, that log sparsity is upper bounded by log approximate sparsity to the power 2. There is a extra log n factor in the relationship. And this is tight, as you can see, I've been saying this. So approximate sparsity of OR is n to the order root n, because the degree of OR is theta root n, and sparsity of OR is 2 to the n minus 1, whatever. So up to polylog n this 2 is tight. Okay, this relationship, this 2 is tight. Moreover, we can say the log n is necessary because we know there is a function whose exact sparsity is theta n, but whose approximate sparsity is just order log n. Okay, so you need to have some log n by log n multiplicative factor or some additive log n factor in your relationship. You can't just have a relationship without any dependence on n. Any constants? 10. Okay, so I have enough time to say, to give you some idea of how the result is proved. So what do you want to prove? You want to prove that whenever the sparsity, exact sparsity is large, approximate sparsity is large, right? So to understand that, we have to understand what large sparsity mean. How will it look like? Like what kind of functions have large sparsity? And once we know that structure that large sparsity imposes, then we would want to use that structure to argue that approximate sparsity is large, right? Before we do that, let's take some examples some concrete examples where we will just try to prove their approximate sparsity lower one. We just want to understand approximate sparsity of OR and not exact sparsity. We want to understand approximate sparsity of OR, let's say. How would you go about proving such a thing? Anyway, we only have one tool in our toolbox, which is random restriction. That's all we know. Maybe one more tool in circuit complexity. So we use random restriction. One way we can do this is choose a random restriction which sets each variable to 0 with probability half and leaves it free with probability half. If we choose such a random restriction and hit OR function with this random restriction, then it will still compute an OR function on the free variables. And since each of the variable is set to 0 and left free independently, we have done this for each variable. We know that with good probability, the number of free variables will be like n by 4 by basic Chernoff count. And moreover, we know that if we have any monomial of degree k, if we hit that monomial with this restriction, this monomial will be killed. It will become a constant with probability 1 minus 2 to the minus k, right? So we'll argue that approximate sparsity of OR function is 2 to the omega root n. We'll do this by contradiction. We'll say let Q be an approximating polynomial for OR functions with sparsity 2 to the root n by 100. Okay. If I hit this polynomial with my random restriction, then the degree of that polynomial will be less than root n by 10 with good probability. Why? Because there are only 2 to the root n by 100 monomials. Each monomial of degree more than root n by 10 will be killed with probability 2 to the minus root n by 10. So we're just a union bound. I know that degree cannot be more than root n by 10 with high probability. Right. But I know that Q, when hit with this restriction, still has to be an approximating polynomial for an OR function on n by 4 variables. So it's just a probabilistic argument. There exists a random restriction such that OR, when hit by that random restriction on n variables, will still be computing an OR on n by 4 variables. Moreover, this polynomial, which should be approximating OR hit with this random restriction, has degree less than root n by 10. So this polynomial of degree less than root n by 10 is computing an OR function on n by 4 variables. This will contradict the degree lower bound for OR function. We know the degree lower bound for an OR function is like root n up to some constant. We can change the constant in analysis, whatever. But this will contradict the degree lower bound for OR function. Okay. This works only with points of approximate. Yeah, we have not studied that scenario. Yeah, okay. I'll take one more example, okay, because these two examples are very instructive. Let's take another example where we want to prove an approximate sparsity lower bound for and composed with 2-bit OR functions. So there's this block of variables, two variables per block. They're computing OR on that block and then taking the AND of all those blocks. Okay. Now note that if I just do the same random restriction process, set each variable to 0 with probability half, leave it free with probability half, and this function will be killed. Because with good probability, both the variables in a block will be set to 0, right? That OR will become 0, that AND will become 0. So we can't do independently set variable to a 0 or leave it free, right? But what we can do is, we can do following. For each block, either set the first variable to 0, leave the second free, or with probability half, set the second variable to 0 and leave the first variable free. What this will do is, the function when hit with this restriction will become just an AND function on the free variables, right? And again, we have a similar kind of statement. Any monomial of a degree k will get killed with probability 1 minus 2 to the minus k, right? And again, we can do that whole contradiction argument and to argue that approximate sparsity will be 2 to the omega n in this case. So note that in this case, I've used the structure of AND/OR function. I've used that there are these blocks and I can play with these blocks. So that insight is needed to prove this lower bound. So I have to look into the function and then come up with a random restriction strategy. Okay. But what we are trying to do is, we are trying to say that whenever sparsity is large, approximate sparsity will be large. We just know sparsity is large. We don't know any other structural information about the function. We just know sparsity is large. We just have to find out some structural information and then use that to prove approximate sparsity. One strategy could be to find the characterization of large sparsity. Whenever the function is large sparsity, for example, it embeds some set of functions. For example, whenever the large sparsity is large, f embeds OR function, or it embeds an AND/OR function, or it embeds some other function. Find some characterization, and then argue for each of the function that approximate sparsity is large. Right? This could be one strategy. Right? It would be very satisfactory because we would know what it means for a function to have large sparsity. That would just mean that we have so and so function must be sitting inside your function. That's why the sparsity is large. And it's a very concrete understanding which can then be used, in other places where we want to work with sparsity. And for monotone function, we can concretely say this, that for a monotone function, either there will be an OR or there will be an AND/OR. Nothing else. Whenever sparsity is large, you can say either there is an OR sitting inside, or there's an AND/OR sitting inside. But for general function, we can't say this. Only for monotone function, we have this characterization. It would be a nice problem to find out for. So morally, that is the case. It won't be AND/OR, it will be some adaptive AND/OR, but I don't want to go into those details. But for general function, we don't have such characterization. What we do instead is we construct a random restriction process which has following properties. So I'm describing this L variable max degree distribution. It's a distribution over random restriction. And it is for a given function f, which says that this row will leave a lot of variables free, L variables free. Second, whenever I hit my function with this restriction, the degree of the function will be the number of free variables, the complete degree possible. And the third condition is, any monomial when hit with this row has, the probability that it will survive, or the probability that its degree will be more than t is like 2 to the minus t. You can see that these properties were essentially the properties that I was using to argue why approximate sparsity of OR was large, or approximate sparsity of AND/OR was large. Right? So I'm just making this note that if I can show that large sparsity implies such a distribution on random restriction, then I can say that approximate sparsity is like 2 to the omega root L. Just by the same argument that we did, the contradiction argument. Yeah. And this is what we do. We say that whenever sparsity is large, we give a random restriction process, which is not very complicated, which implies existence of such a distribution, where L will be like log sparsity by log n. And as you can see, you will get approximate sparsity lower bound, which will be like 2 to the omega square root of log sparsity by log. And we'll get our relation. Okay. Yeah, we have some more results about relating L1 norm and exact L1 norm and approximate L1 norm, and looking at some generalizations. So the report is on ECCC. You can check it out. Yeah, thanks. Yeah, this is what we can ensure. I can ensure this. Huh? No, it's not needed. I just need high probability event. Yeah, it's nice that it's
highly correlated and all, right?
they're correlated. Yeah, that's how we are selling it.
Yeah.
If there are no more questions, let's thank the speaker.